Science for pigeons. Water waves. Water waves are transverse. Think of ocean swells. Their energy travels horizontally, but the water itself moves up and down. This perpendicular motion defines transversal waves. These waves carry energy, not water, and light waves work the same way. They kind of look like an S, like that. All waves, whether they're transverse or not, can reflect. For example, a shout echoes off a wall, and a water wave bounces off a seawall. Reflection simply changes a wave's path. Transverse waves have some clear features. The highest point is called the crest. The lowest point in a transverse wave is called the trough. And displacement is any point's distance from the calm middle line. Amplitude is the maximum displacement from the middle to the crest, or also from the middle to the trough. When waves meet, they combine. This is called superposition. So imagine two ripples on a pond colliding. Their heights add together at that instant. Afterwards, they travel on unchanged. Two crests meeting create a taller crest, and two troughs meeting create a, surprise, surprise, deeper trough. If a crest meets a trough, they subtract. They can even cancel out, leaving momentarily still water. This phenomenon is used in noise cancellation earphones. Okay, so let's speak about light waves. Light is an energy wave, as far as you're concerned. The sun, a candle flame, and a light bulb, these are all sources of light, so we say that they are luminous sources. And light waves always travel in straight lines. Like water waves, light is transverse, so it has that characteristic sinusoidal pattern like that, like a sine wave, if you've ever seen it. Its oscillations are perpendicular to the direction of travel. This transfers energy from the source to the observer, and light reflects. And this is the principle behind how mirrors work. But light is fundamentally different. Water waves need particles to vibrate, but light does not. It doesn't actually need a medium to propagate. That's why it can travel through perfectly empty space. This is crucial. Sunlight crosses the vacuum of space, and a vacuum is empty. It contains no air or particles. There, light actually achieves its maximum speed, which kind of makes sense because there's absolutely nothing in its way to slow it down or stop it. And what is the maximum speed of light? Well, if I say 300 million meters per second, that sounds awfully impressive, but how fast actually is that? That would be the equivalent of circling around the Earth roughly 7 times in every second. And to reach the moon, a little bit over 1 second to reach the moon. This universal constant, the speed of light, means that sunlight takes 8 minutes and 2 from where the sun is, which is 150 million kilometers away. Nothing travels faster. To contextualize that, if you were to set up some kind of magical road between the Earth and the sun, and to travel at the speed limit that most cars are permitted to travel at, it would take about 200 years to reach the sun. That's how far away the sun is. When light passes through matter, like air, or water, or glass, it slows down. Yet, its speed remains astonishingly fast. To our eyes, the journey appears to be instantaneous. So, let's speak about reflection and refraction. Reflection and refraction. Light reflects, like bouncing off a mirror, or it refracts. Both involve a change in direction. So I want you to imagine a caveman, or a primitive person, if you like, an ancestral human. How would you demonstrate to them reflection and refraction of light? For reflection, go to a lake, on a clear lake, on a sunny day, and look into it. You can see your reflection. For refraction, pick up a stick and put it in the lake and watch as it seems to bend in the water. Reflection bounces light. A mirror's smooth, shiny surface gives a clear reflection. This is called specular reflection. But there's another kind of reflection. Sometimes, like the kind of reflection that makes ordinary, everyday objects visible to your eyes. That's called diffuse reflection. Diffuse reflection. A rough surface scatters light in all directions. This is diffuse reflection. Okay. The law for how to predict what direction a light is going to go in is quite simple. It says that first, imagine that there is this sort of like, there you have your flat surface, and now imagine a line called the normal line, which is an imaginary perpendicular line at a right angle to the flat surface, the mirror surface. And now imagine that the light ray comes in. This is the incident ray. That will have an angle with the normal line down the middle. The reflected ray will have the same angle as that, which makes sense because if you were to shine the torch directly perpendicular to the mirror line, then the light ray should bounce directly back. It should bounce directly back. Okay, so what about refraction? Refraction is the bending of light as it passes between different materials or media. For example, going from glass into air, or air into glass, or air into water. Light bends because it changes speed, simply, as we say. And the rule for predicting how this works is consistent as well. If light bending into a denser medium, like from air into glass, slows down and bends towards the normal, it would make sense that if light were to pass from air into glass, it would slow down. That makes sense because glass is thicker and denser than air. But the fact that it bends towards the normal, that's something that for now you'll have to just remember, because it's harder to make sense of that fact. When light bends into a less dense medium, like from glass into air, which is the opposite situation, it would do the opposite. So it would speed up and it would bend away from the normal. It would bend away from the normal. Okay? So one way that you can remember that is if it goes from glass into air, then air begins with A, and away begins with A as well. So if it goes from glass into air, it bends away from the normal line. Okay, so now let's think of a car. If its right wheels drive in onto sand at an angle, they slow first, and the car turns right towards the normal. When the wheels leave the sand, the right side speeds up first, turning the car left away from the normal. And if the entire car hits the sand straight on, it slows evenly and goes straight. This is an analogy that can help you think of how light is behaving when it's diffracting. But the mnemonic that I mentioned earlier is also handy. So now let's talk about how we actually see things. We see because of light, of course. Light bounces off everything all around you. A light bulb is luminous. It makes its own light. And just literally my face is luminous because it reflects my face luminous? No, my face is non-luminous because it's reflecting light from the lamp behind the screen. That reflected light must enter your eye. A simple pinhole camera shows how. Light always travels in straight lines. It streams through a tiny hole, rays from the top and bottom of an object, cross inside the dark box. This creates a sharp but upside down image. Your brain actually flips the image, which is upside down in your retina. Lenses focus this scattered light. A convex lens, which bulges outwards, which is actually on the shape of the lens on your eye, bends light inward. It converges rays to a single point, and for you, the single point is at the back of your retina. Your eye, actually your pair of eyes, work like sophisticated cameras. Its clear front window, which is called the cornea, is convex, so it's pillowed outwards like that. It does most of the focusing. Directly behind it sits a flexible convex lens. This lens fine-tunes focus by changing shape, allowing you to see things near and far away from you. And the colored iris, which is either brown or blue or green, adjusts the pupil size, which controls how much light your eyes actually take in. The focused image forms a retina at the back, as I said before, and the retina is lined with light-sensitive cells, which are called the rods and cones. Light carries energy. Vision is the process of capturing that energy. Light energy transfers from a source to an absorber. In your eye, the retinal cells are the absorbers. In an old camera, film absorbs it, although we rarely use these anymore. But in your phone, or the phone that you're looking through right now, a digital sensor does this. This absorbed energy triggers a change. In your retina, it alters chemicals, creating electrical signals for your brain. And in a digital sensor, light generates a tiny electrical charge. The processor reads this pattern of charges, and that pattern becomes your photograph. Okay, now let's talk about how color works. So white light contains every color. Okay, a prism or a raindrop can actually split white light into its component colors. This splitting is called dispersion. It's called dispersion, and it reveals the spectrum, which you can remember through the word Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And each color that you see has a frequency. Frequency measures how many light waves pass by a fixed point each second. Red light has a very low and slow frequency, whereas violet has a high and rapid frequency. The colors shift from low to high frequency across the rainbow. Now, how can we remember that red light has a low frequency and violet has a high frequency? Well, you may have heard of infrared and ultraviolet, because if our eyes were advanced enough, we could actually see the kinds of light that have an even higher frequency than violet, and we could see the kinds of light that have an even lower frequency than red. Those are called infrared and ultraviolet. Ultra means above, and infra means below, so you can sort of piece it together that way. Colored filters are selective. A red filter, for example, transmits only red light. It absorbs all the other colors. So despite its name, red light is actually the only one that gets through, even though it's a red filter, right? Colored objects behave similarly. Blue denim reflects blue light and soaks up all other colors. And a white t-shirt reflects all colors, whereas a black jumper absorbs them all. Okay? So, colored light dramatically alters what we see. We know that from experience. Imagine a red football boot with green laces under white light. The boot reflects red, the laces reflect green. Now, shine onto that boot only red light. The boot still reflects red, appearing red, but the green laces have no green light to reflect. They absorb the red light and appear black. Under pure green light, the opposite occurs. The laces glow green, but the boot absorbs the green and turns black. The object's color depends entirely on the light that it receives then. Now, having spoken about light, let's speak about sound. Okay. Sound is not a transversal wave, unlike water waves and light waves. Sound is what's known as a longitudinal wave. So, you know a slinky toy? Let's think of a slinky's push and pull. The vibrations move parallel, the waves travel. They resemble a barcode, but the lines are more squashed together at parts and more further apart in other parts of the wave. This is how energy is transferred in a transversal wave. Sounds must travel through a substance or medium. Air, water, and steel are all fine. Sound can travel through all of these, whereas a vacuum-like space is silent. There's no particles to transmit the sound waves. Vibrating objects create sound, but it's not always sound that we can actually hear, right? But for the sounds that we can hear, like those generated by your vocal cords or a guitar string, this is the result of them shaking. They create sound waves. This pushes particles together into compressions, and these dense regions pulse through the medium. As mentioned earlier, sound reflects, creating echoes. This is reflection as applied to sound waves. A shout bouncing off a canyon wall, for example, is a very classic echo that you can think of, but it also absorbs. Sound can also be absorbed. Soft materials like foam and carpets soak it up, whereas hard materials bounce it back, which is something that you need to bear in mind for sound design if you're recording yourself in a studio, for example. What about the speed of sound though? Well, in air, It's a little bit over 300 meters per second. I think it's something like 340, 330 meters per second, something like that. But it depends on the density of the medium that the sound is traveling through. If there are more particles in a small amount of space, then they will knock into each other faster and the sound will travel faster. So it will race through solids like railway tracks and will move quite well through liquids like water, but it will go at a crawling speed through gases like air. And of course, light is vastly faster than sound. It's almost 1,000,000 times faster than sound, actually. Frequency, the frequency of the longitudinal wave determines the pitch of the sound, how high or how low the sound is. It counts the amount of vibrations per second, and you measure it in hertz, Hertz. High frequency means a high pitch, like a whistle, and low frequency means a low pitch, like a drum. Your ear translates these vibrations into the sounds that you hear. So, with that said, let's speak about hearing. Hearing starts with sound waves entering your ear, for sure. They strike your eardrum, making it vibrate. These vibrations move 3 tiny bones. These bones act as levers, and they amplify the vibrations. The final bone taps a coiled liquid-filled tube called the cochlea. Inside that, thousands of microscopic hairs sway back and forth, and different pitches sway different hairs in your cochlea. This movement ends up creating electrical signals. It's so remarkable if you think about it, how these work. These signals travel up the auditory nerve, and your brain interprets them as sound. Hearing depends on frequency or pitch. As I said earlier, you measure frequency in hertz. Human hearing typically spans from 20 hertz to 20,000 hertz. And if you have a rumble that is deep enough and lower than 20 hertz, you would call that infrasound. And if it's above 20,000 hertz, like what a dog whistle generates, that's called ultrasound. Many animals can actually hear well beyond our limits. Dogs actually hear high-pitched squeaks, and bats famously use ultrasound to navigate. Dolphins as well communicate in complex clicks that we can't hear ourselves. Okay, let's now speak about energy and waves last of all. Waves can transfer both energy and information. A shout carries energy to your ears and also the information from your voice. Sound is a pressure wave, as we said earlier. It moves energy from vibrating particles in the air, creating tiny pressure changes. And a microphone, as you can see in front of you, captures this. Sound waves vibrate its thin diaphragm within it, converting motion into an electrical signal. This signal can be recorded and stored, and a loudspeaker reverses this process. It turns an electrical signal back into diaphragm vibrations. The vibrating diaphragm pushes the air, recreating the original sound waves. Ultrasound, which was mentioned earlier, is the sound with a frequency above 20,000 hertz, well beyond human hearing. It transfers energy deeply through matter. One famous use of it is ultrasonic cleaning. The high-frequency waves are sent through a liquid bath, and they create microscopic bubbles that form and collapse in tight spaces, which scour away dirt trapped on things, and this effectively cleans intricate items like jewelry or camera lenses. But it can also transmit energy into the human body, and some physiotherapists, in fact, try to use it to target deep tissues like muscles and tendons. However, strong scientific evidence for its clinical effectiveness remains limited at the moment. Alright, so that wraps up today's lesson.